mass M1 and mass M2 in a coiled spring between them. We release this spring. Some undetermined time interval, M1 moves through a distance or displacement. We'll call delta X1, and M2 moves through displacement delta X2. It being an isolated system, what's the ratio of the second mass to the first? Now, the answer everybody pretty much gives, and it's correct. Why is that answer correct? So question, why? And which mass felt the greater force? Well, some people said, well, the one that moved further. Other people maybe said, well, the one with the greater mass. So, by Newton's third law, the forces were equal and opposite. Now, if the forces were equal and opposite, anything else could have been equal and opposite. Or anything else that we could compare. Okay, so I said a bunch of stuff I thought I recorded. Okay, so there was a suggestion at this point where we consider energy. And to summarize what I said is, well, you don't know the nature of the collision. Okay. First place, you have a potential energy here. If this is an ideal spring, then you probably have conservation of kinetic energy, or conservation of energy. Your potential energy in the spring compares to kinetic energy of the two masses. Okay, so that's kind of worth thinking about. In other collisions, kinetic energy might not be conserved, and even in this, well, kinetic energy is certainly not conserved. There's no kinetic energy here, spring recoils, and now you've got kinetic energy. And if you start thinking about the ratio of kinetic energies, it's a little harder than thinking through what we're doing. Okay, so I'll kind of put that off to the side, but it is something you want to analyze. It's something you're going to have to analyze. What can we conclude about the accelerations? Okay, forces are equal and opposite. So what can we conclude about the ratio, let's say, of A2 to A1? It's the acceleration of the second to the acceleration of the first. Okay, well, the first answer I got, I won't name the culprit, but the first answer I got was, well, wouldn't it be proportional to the masses? Okay. And my answer was, well, you mean the greater mass would have the greater acceleration? And immediately go, oh yeah, it's going to be inversely proportional. Okay. That should be obvious. The forces are equal and opposite. So the ratio of the accelerations ought to be inverse to the ratio of the masses, except of course, it should be negative because the ratio of the accelerations has to be negative. One acceleration is positive, the other is negative, right? And down here, I should have done that too with a minus sign. Should have been a minus sign. Because delta x1 and delta x2 are different directions. I could have used absolute value signs. Could have said the ratio of the absolute value of the ratio of the accelerations is the absolute value of the ratio of masses. Okay. Alternatively, the ratio of the masses can't be negative, so the absolute value of the ratio of the masses is just the ratio of the masses. So you might want to think about that. Important thing to understand. Important sort of thing to understand. But as applies to this situation, now we know that the accelerations are in this ratio. At every instant. Well, then can we say that V2 over V1 equals M1 over M2? Well, the velocity is the integral of the acceleration. If the accelerations are always in this ratio, then the velocities will always be in this ratio. Make sense? So potential velocity is this interval. And forces act at the same time, they act simultaneously over the same time interval, we can draw this conclusion because I have enough stuff to write the expression. Do this. What I can say is A2 is magnitude of M1 over M2 times A1. Say this. Again, A2 is negative M1 over M2 times A1. So if I'm finding A2 of T, I've got to integrate A2 of T. I haven't written that out explicitly. It should be obvious. And in integrating A2 of T dt, I'm integrating negative M2 over M1 times A1 dt. So it all works. Okay, well, what we're trying to conclude is that M2 over M1 is negative delta X1 over X2. Because that's what your intuition told you. Okay, well, again, what we're trying to conclude is this, which is what everybody thought after they thought about it. Okay. Delta X is the integral V of T dt, right? I'll let you figure out how to take the intermediate steps. But I'll just say that if you integrate V1 of T over the integral V2 of T, it's got to give you negative M2 over M1. And you can write that out. You work it out. Now, the intuitive part of that is simply that the forces are the same. So the accelerations are inversely proportional to the masses, and everything else follows. That means the accelerations are inversely proportional to the masses, so that the velocities at every point are inversely proportional to the masses. And that's because the forces act through the same time. And then it follows this plate through exactly the same time. Okay. A good picture now. It shows F net increasing some maximum to zero, decreasing some maximum to zero. during some time here. Okay. Does that realistically depict what happens with those springs? Okay, so the question I pose is, can both of these graphs be accurate? The same system. Turns out that, well, if x is a linear function, t maybe. Okay. But you know, for two springs, the force is going to be changing constantly as the springs fly apart. Okay. Less and less force. So we know that for two springs, the force looks like this. That means the acceleration looks like this, means the acceleration isn't constant, meaning x doesn't change linearly with t. Okay. So can't both be so. That's for the spring. That force is linear and decreasing with x. It's linear, but b which is dx dt is not. Okay, since the force isn't constant, dx dt is not constant. This phrase you'll hopefully get the idea. So that this won't be constant. What's going to happen is the graph is going to look like this. The graph is going to go from a maximum to zero. Okay. But x is going to be changing faster and faster with respect to t. Okay. So your net force might look like this. Whatever it looks like, what's the area under this graph represent? What's the area under this graph represent? Part of that as I did it, but the answer is somebody got it. The area of this one represents force. What I explained was, well, it's the integral of F net dx. That's what we're finding net force. Okay. On any tiny increment, you have an interval of motion, an x interval, and a force that's more or less constant. So in every one of these increments, the value of F net is multiplied by the length of that small increment. And you add them all up. It's your remotion, etc. Okay. You want to think in terms of that. And for sure, what an interval tells you. Okay. Up here, the area under this is what interval. Somebody told me pretty quickly that this area We know what the name of that is? Okay, hang on. Give you a chance for glory. So this represents F net, F net dt, that's impulse. Now the word I got first was momentum. It's change in momentum. Okay. Now, when these things fly apart, the impulse of one, the impulse one of them feels is equal and opposite to the impulse that the other one feels. Two impulses are equal and opposite. Okay. Which means that their changes in momentum are equal and opposite. So that you have conservation of momentum. That's important to understand all that before you start. Where we go? Before you start falling back on this. That's all you know. You don't know it. Although you probably pass. Okay, if you're good with it. Okay. You're not going to do well, real well. Because it goes back to the fundamentals. This is a result of the conservation of momentum. Now, if see, if the two blocks are on an incline, frictionless incline, the net force is equal and opposite. Okay, assuming that F elastic is positive, because I don't have an arrow over it. The F net one would then be negative F elastic. Okay. But then you'd have plus M1G cosine theta, which I think you know perfectly well. People try to say that, but you want to separate it out. You kind of confusing the F elastic with the M1G cosine theta, one at a time. Okay, you know both of these forces are acting, and if there's friction, there's also friction. But we said friction. Let's just keep it simple. Okay, F net 2 is what? Well, F elastic plus M2G cosine theta, right? Now, question. These forces equal and opposite? No, among other things, M2 presumably different than M1. And even if it isn't, they have the same sign, they're not opposite. Okay, even if M1 was equal to M2, this wouldn't be equal to the negative this. Okay. the word if. This was not isolated. If you confine the system just M1 and M2, it's not isolated because gravity's poking its nose in there. So if you think that these things are going to, if you think the displacements here are going to have the same ratio, well, the inverse ratio of the masses, like we saw an isolated system, it's wrong. It's not right. So, okay, so the delta X2 over delta X1 is not going to equal negative M1 over M2. Okay. This is one illustration of a non-isolated system. Now, even if the incline is horizontal, are the friction forces equal and opposite? Well, it turns out maybe they are if the masses are the same. Okay. If you have the same mass and the same coefficient of friction, then this one's moving this way, so friction's going this way. This one's moving this way, so friction's going this way. Okay, so if they're moving in opposite directions, then you could still consider this to be an isolated system, but you got to include the friction in the net force. Okay, but only if they have the same mass. If they have different masses, there's no way that the frictional forces are equal and opposite. Also, if they're already moving and you release the spring, unless they reverse, one of them reverses direction, it's not going to be isolated because friction will be acting in the same direction for both of them, and it won't be equal and opposite. I try to digest that. Gives you insight, if you digest it, that I wish I'd have had when I took this course. Beat my head for about 6 hours on what an isolated system was. Okay. Finally made an impression, but gave me a couple of minor concussions. I don't know what that. Okay, well, anyhow, get the idea. Okay, so now we did this on a dynamics track, and I don't have a good way to set this up, but I've got a magnet strapped to this end of this card and a smaller magnet strapped to this end. Same magnets we use when we're doing the cars, Ford cars. These things come together and there's a repulsive force and it gets greater and greater. And then the repulsive force becomes so great that they start moving apart. Okay. So the force exerted, let's say the positive direction this way, the force exerted on the cart on this side, it's going to be positive. So there's your net force versus time. Assuming your system is isolated and there's no slope to your dynamics track, because if there is, you get this empty cosine theta phase. Okay, now, if this would be your time, okay, not really, the force could be skewed one way or the other. It'd have a long tail this way or a long tail that way. And you kind of think a little bit about how it's likely to work. The magnet forces increase very rapidly. Okay, and we've observed those. Okay. You've had data on that, hopefully you've analyzed it. And actually people did fairly well with that question on the test. So we get the idea of that force. Now we put it into this context, it's a little more difficult to deal with. There are calculus tricks that we could use that we're not going to use in much for semester. I'll refer to them just keep your brains working a little bit on what the calculations. Okay. So anyhow, that's what typical interactions or golf club with a golf ball. Got that? Question. Okay. So, you have this sort of thing, but there's almost always a skew. Compression. The force versus position would tend to be symmetric. Force versus time is a little more complicated.